Hello, everybody. This is Jason Ren. I'm currently a professor at the Department of Civil Environmental Engineering and the Ellinger Center for Energy Environment at Princeton University. I'm also serving as acting director and associate director for research at the Ellinger Center. It's a great pleasure to present at this conference, and thank you so much, Jerry, for the invitation. It's great to actually see everybody virtually. So what I will talk about today is to really links to the broader concept of water energy nexus, specifically how we use like low-cost renewable energy for resource recovery in water, but also how do we actually recover energy out of waste treatment process. Before I start, I want to just spend a minute to talk about Ellinger Center. Ellinger Center is relatively new center that was established at Princeton a few years ago, focusing on technological solutions and analytics for solving energy and environmental problems. It strives to have interdisciplinary nature, where we have about more than 100 faculty affiliated with the center across 44 departments. And we focus on the following 6 buckets, even though we do many, many more things related to energy environment. And also not only on the science technology side, we also have an affiliate program where we interact with industry partners. And also we do, say, public affair and environmental climate research in collaboration with Princeton School of Public International Affairs and the Princeton Environmental Institute. So with that said, as a starting slides, we all know like we used to cover extreme events like say hurricanes, flood, drought, or fire. We see them very often right now. Like every year, we will see all these multiple events that are happening around the world. And we certainly realized that this would I guess unusual weather pattern or climate actually change related to the fossil fuel use in the past century. So in an effort to decarbonize the different industrial sectors and decarbonize our society to actually maintain a sustainable, I guess, economy and our life, we can see like there's many different sectors we can decarbonize, right? We can reduce the fossil fuel use, we can enable a circular economy. And among them, certainly energy sector has the most promise to decarbonize, and certainly followed by transportation industry, forestry, and other things. And this industry has very largely actually in the good trajectory on decarbonization. You can see from the new capacity, basically the new installations of power generating capacity in the past few years, you don't really see coal anymore, and nor oil or other non-renewable sources. And you do see some natural gas still, but it has lower emissions associated with, let me compare with coal. But you see more and more the blue section of the bar chart is really, you see the increased actually installation of renewables. It's certainly include the solar, wind, and other actually renewable energies. And more importantly, that what drives the market is not only because of our climate change conscious and the actually all the different efforts made to decarbonize the society, but also the cost, right? You can see this is a sort of a study demonstrate really the cost of all the different type of renewable energies, especially solar and wind, has really gone down dramatically by orders and magnitudes in the past decade or so. And you see right now, the cost of the renewable energy at certain area is 2 cents to 7 cents per kilowatt hour. This is actually below the fossil fuel based electricity. And in some places, like California, it can actually get to negative at a certain period of time, right? So with that as actually a good incentive to use the renewable energy for different things, that's a sort of, we got an energy source, the electricity. But how about carbon? I mean, if we want to produce, say, renewable fuels or chemicals and things like that, we also need a carbon source, right? And in that end, you see the, traditionally, we basically use biomass, right? We rely on, biomass or plants to absorb sunlight, doing photosynthesis, and then we'll process the biomass, whether it's the cellulose, whether it's the soybean, whether it's other algae, and to actually produce different type of fuels and chemicals from biomass. But recently there have been like a great actually interest and progress in not using biomass, but rather to using the renewable energy. For example, if you do electrolysis, you produce hydrogen, supposedly a very low cost hydrogen, but also to take the carbon dioxide, say from point source or even air capture, to reduce carbon dioxide into this new type of chemicals and fuels. So that's a sort of it's not only solving the, I guess, the energy issue, but also you directly tackling the CO2 emission issue, right? To make it carbon negative. So there's certainly merit on it based on sort of the efficiency. You can see from the slides where you see the traditional photosynthesis actually has very low efficiency, and it's like only 0.2%. And but if you see the algae is a little bit higher, 1.5%. But if you look at the products where you have an electrolyzer and you get energy from the solar panel, and then through that, you actually can get a product at about more than 7%. So it's like an orders of magnitude higher in using this process as compared to traditional photosynthesis routes, right? With that, you actually see hydrogen, like I mentioned in last slides, is becoming a very good alternative or even more complementary energy carrier or material precursor for renewable energy and material production, where you see, because certainly we have a lot of needs on renewable electricity, but there's certainly great needs on like storage because the intermittency of renewable energy. And also, if you only have electricity, you won't be able to replace fossil fuel in a very specific sector, for example, fertilizer or chemical industry, where they still rely on heavily on fossil fuel-based feedstock. So in this case, hydrogen is a great building block to replace those type of fossil fuel use as well. So with that said, we collaborated with Greg Rao to sort of, as a leader in this field, to look at what are the potentials of using renewable electricity to generate carbon negative hydrogen, and then using hydrogen for different type of exciting applications. And the results was actually pretty exciting. You can see by using those processes, different renewable electricity, you actually be able to potentially actually remove hundreds of gigatons of CO2 per year. So that's actually a very good trajectory in terms of renewable hydrogen. And on the other side, there's a lot of studies on looking at the wet waste or waste materials, it's organic waste materials, that how do we convert those into renewable energy and the fuels. So this is actually a report was recently published by Bioenergy Technologies Office at DOE. And then they basically look at the different potentials and say, well, this is actually the system has the waste we generate every year can have a big potential in terms of energy and the resource recovery. For example, by converting this wet waste, gaseous waste, we can replace about 11 billion gallons of gasoline per year, which is about 15% of our annual gasoline production in the United States. All right, so with that said, I want to give a few examples of my lab has been doing in terms of generating renewable energy and using energy for resource recovery. So the first sort of concept we had was, if you go back to the artificial photosynthesis, which is certainly a very popular topic right now. And but in many cases, if you have an anode, say you would have a say water oxidation and produce oxygen, and the cathode will be hydrogen production, right? So in that case, in most cases, you would need two catalysts on each side, one for water oxidation, the other for proton reduction. And that you generally need a bias, right? More than generally around 2 volts, because you have a theoretical band gap of 1.23 volt, right? So you need an external voltage. And there are certainly dual junction gap, dual junction actually electrolyzers or catalysts, but right now they are quite expensive, and corrosion has been a major issue, and it's quite a complicated system. So in this case, what we proposed was that if we can actually replace the water oxidation in the anode with wastewater, which basically we, rather than oxidizing water, we oxidize waste, organics in wastewater. So with that, we effectively actually reduced the band gap from 1.23 volt to about only 0.12 volt by more than 90%. So in that case, if you actually, you can see most of actually the commonly used catalyst would be able to straddle on both actually bands, right? The voltage potentials. So that's going to give you a very good, promising approach to not only solve the, say, the energy needs of electrolysis, energy problem by making it more independent, but also you solve the water problem, because you don't have a pure water everywhere. It's not easy to get. It's expensive to produce in certain places. Rather, wastewater is generated wherever actually there's human being, right? And you have to treat the wastewater anyway. So you actually solve the water problem as well. So in that case, so this, like I said, we will replace actually pure water in the anode and with this wastewater by using the biocatalyst, basically bacteria. So here I'll show you sort of an early study we did. We compared a microbial electrolysis where you use bioanode for wastewater treatment and a regular cathode for hydrogen production, for example, like stainless steel, or platinum, or cobalt, or nickel specifically. But also you would, we replace this with actually anode with a photocathode. It's a pretty commonly used one. Gallium indium diphosphide as a photocatalytic cathode. So you can see with that, where you would be able to produce a current without any external bias, right? You get about 0.59 milliamps per centimeter square. So you get a self-sustaining hydrogen production. So nothing actually you apply outside. As compared to that, our regular MEC cell did not produce any current. And then if you do apply a small current, a small voltage outside of voltage, you it's still far less than traditional water electrolysis. You get about 1 milliamps per centimeter square in MEC, but you got a more than 10 times higher current on that in this photocathode combination with bioanode. All right, and then recently we said, well, the catalyst we use is still pretty expensive, and how do we scale it up, especially linked to wastewater treatment? So in collaboration with San Diego State University, Professor Gu Jing's lab, we were trying to actually develop this process to actually use her very interesting cathode, where she coined the term called a Swiss cheese interface. You can see from the characterization, whether it's molybdenum sulfide or whether it's platinum, you get this sort of a very porous structure that does not really need any protection layer. So it does not really degrade in at least in the hundreds of hours we run in the system. But also it does not really what let's say need that protection layer. So that's a sort of in a way that give you a very promising result when we try to put it into our system. So this is sort of a example we try to show you, where there's a basically a reactor. I'm playing this video now. The reactor, you can see that once we have sunlight stimulated in there, wastewater in the reactor, you see actually right here, there's a pretty good hydrogen production, continuous bubbling up, right? And you see from the right graph, you see where you have good cycles between light and dark in terms of power, in terms of current production, and also you see the cyclic repeating, pretty stable repeating pattern on the anode side and also on the photocathode side. And then we got a pretty exciting result, where if we use actually those black silicon based photocathode combining with our bioanode, you will get about 25 to 30 milliamp per centimeter square. And on the right, you see we actually use this system in real brewery wastewater, so beer wastewater. And you see X was the time, Y was the current photocurrent density. We got about more than 20 milliamp per centimeter square. That's pretty high current, and at a very stable rate for more than 90 hours. And it can still continue, but we just run out of the wastewater. It's not about the photocathode problem, right? And when you compare the studies, certainly you see from either stability in terms of how long we can run, in terms of the conversion efficiency, in terms of current density, we all achieved pretty good results. And one thing we want to mention, the photocathode is certainly quite smaller compared to the bioanode, which is a brush system. But in reality, that was supposed to be, because you do need a high surface area and a volume to treat a lot of wastewater, because it's smaller. It's a slower process because it's a bio system, but it's coupled with a smaller photocathode. So that's actually worked out pretty nicely. All right, with that said though, I mean, sunlight is still sunlight, right? If we use photocathode, which still has certain barriers, as many of you are expert in this area, is that we have some difficulty at scaling up the photocathode, as well as the durability and actually the material we use in the photocathode. But recently, we also developed a new decoupling strategy. And in this case, we developed a tailored power management system. So this yellow box, basically, you can see. We use this system, so basically where it has an energy harvesting circuit for the anode, where it collects the energy generated from the organic chemical degradation in the anode, still using bacteria. But it's also in situ actually converts the low voltage generated from the anode, like 0.3 volts, to a higher voltage at more than 2 volts, okay? And then the second part of the PMS system, we have this electromagnetic transformer that would transfer that energy into the cathode for hydrogen evolution, or water splitting in that case. So in this case, we don't need light anymore, and we don't need external voltage either. So we basically accumulated in situ energy generated from the anode, boost it up, and that would enable hydrogen evolution. So this is another video you can see. Again, very stable, continuous bubble, hydrogen bubble generation on the cathode. So the interesting part of this is, if you have an electrolyte, if you traditionally have one electrolyte connecting with anode and cathode, like using an exchange membrane, you won't be able to do that because thermodynamically it's not possible, right? That's why you need an external boost. But in this case, because you use this electrode circuit to decouple the process, you would be able to realize this uphill reaction to generate hydrogen spontaneously. So that's why I feel it's a true spontaneous hydrogen production in this case that make it very interesting. So some result here, I mean, you can see on the left where the energy generation part output, certainly it has a lower voltage, right? But since we boosted it also using our PMS, it has a much higher voltage that allows hydrogen evolution. but certainly we sacrificed on the current side, so current is lower, right? But if you see the efficiency is actually pretty nice, where you see the efficiency around the whole energy harvesting system was about 70%. The flyback converter we use is about 40%, and the TMS overall is about 35%. And if you look at the energy flow chart, say for one system, we generate say 0.78 milliwatt energy, and about 1/3 went to hydrogen, 1/3 went to the circuit, 1/3 went to the converter. So overall, we feel this is a very exciting process because it's cheap. It's actually very easy to make, and yet it allowed very actually instantaneous, spontaneous actually hydrogen production. That's why this study was featured on the cover of EES journal. All right. So talking about hydrogen, then we want to say, okay, we deal with a lot of gas, right? Hydrogen is a gas, CO2 is a gas, and certainly in traditional environmental process, we use oxygen and methane and things like that. So we have to develop an efficient gas separation or gas extraction system. So in this case, we try to look at the different membranes, basically gas diffusion membrane, to either efficiently extract the gas product of the water or efficiently inject gas substrate into water, right? So I'll give you one example. This is ammonia extraction. Ammonia is a gas, and there's also fertilizer. So if you look at the sort of electrochemistry side, on the anode, we have this ammonium-rich wastewater, we call centrate. And then once you have hydrogen production on the cathode side, you have OH accumulated on the surface of cathode, right? And in order to balance the charge, so this positively charged ion, proton or NH4+, gonna migrate into the cathode. And once they migrate into the cathode, hydrogen gonna become hydrogen gas, and then ammonium gonna do a phase change because the pH is much higher on the surface of the cathode to like a pH 12. So it's actually enable a phase change to directly extract the ammonia gas out as well. So that's actually a very interesting concept. So this is a membrane on the bottom. You can see we produced. Another very interesting material I want to show you is based on trees, right? I spent many years in Colorado. This is beautiful Rocky Mountain National Park. But because of climate change, the pine beetles were able to survive the harsh winter in the mountains. So they keep actually killing the pine trees in the past few years, right? And once you have that tree, it's dry, it's easy to cause wildfire, right? So in that case, we were working with Professor Liangbing Hu at the University of Maryland to say, well, is there a good way we can actually use wood material for different water energy applications? So certainly there are many actually applications have recently been developed, like certainly you can do filtration, catalysis, absorption, producing renewable energy, doing water desalination, right? I'll give you a few examples what we did. One is, this is an early study we did where we work with Professor Hu's group, like we were able to use this kapok tree, where it's like a hollow fiber. They have this hollow wood fiber. So we're able to double the surface area where bacteria can attach, right? And you see the bacteria outside, you see bacteria inside. So we're able to basically double the electricity production out of our systems. On the other side, we further took advantage of the pore, the hierarchical pore structure of the wood, to actually not only using it as electrode once we carbonize it, but using as a filter. So it's like a microfiltration filter. It's a wood filter. So in that case, when you put it into microbial electrochemical cells, you would not only generate current by serving as an electrode, but you will serve as a filter to filtrate water. So you actually get a much higher quality of water effluent out of that system. And also recently we developed this what we call a wood membrane for efficient desalination system, like a thermal desalination. And this certainly can be used for solar desalination as well if you can actually implement that. That's something actually we're working on. So in the membrane distillation process, you see the wood. So horizontal side direction was actually the growth direction. You see they have much bigger pore size. But on the actually vertical side is a cross-sectional section of the wood. It's horizontal, if you put that way. And through this actually process, you see if you apply hot water on one side, cold water on the other, the wood is essentially a very good insulator, right? It blocks heat, right? So you would not have, you have very good actually insulation or low thermal conductivity. But then on the other side, you have this pits. And this pits at about micron size, if you make them hydrophobic on the surface, they would allow vapor or water vapor to pass through, but not water itself to pass through. So in that case, you block the heat, you have much higher thermal efficiency, and you have a good actually flux on water vapor that allows desalination. So that's what you say, actually we compare the efficiency and see it's actually pretty good in terms of permeability, in terms of thermal efficiency and the flux compared to commercial polymer membrane. And another good side of the membrane is that it's made of wood, right? So wood would capture CO2 out of air, so potentially it's much more carbon efficient, potentially even carbon negative compared to traditionally polymer-based membranes. All right, so I'll spend a few minutes on the last section of the talk about the process, right? One actually platform we've been using in the past actually more than a decade was called the microbial electrochemistry platform, where you basically when you insert an electrode, bacteria would be able to attach on the anode. This is on the left is anode, using it as an electron donor. So the bacteria would be able to oxidize anything they can eat, right? So wastewater, hydrocarbon, ammonia, and many other things. And they wouldn't be able to transfer electrons out. So if you directly use electricity, you can call it microbial fuel cell, but more and more people develop a different function. For example, if you use electricity to actually reduce CO2, then you would be able to produce a lot of different fuels, which I'll show you in a minute. And also in the middle, you become a microbial battery on the anode and cathode. So you would be able to generate internal potential in between, where you actually can desalinate salty water. So sodium will move on one side, chloride will move on the other. So you actually achieve water desalination. So it's a very flexible platform that we can use performing electrochemical research. All right, several examples. So this is one way we do it. So this is the work funded by rnal. Basically, they have this black liquor, basically the wastewater generated out of ethanol fermentation. It is really black, very high concentration. And we were able to use this microbial electrochemistry platform to separate on the cathode. We generate hydrogen. We were able to precipitate the cations out. And then in the separation stage in the middle, like I said, you would have a potential, right? You take advantage of potential to separate the ions, you can recover them. And on the anode, you take advantage of the low pH to actually precipitate lignin and then degrade organic acid. So overall, all three type of chambers would perform their own role to recover the different resources we want to recover. And also you can see the water got much cleaner as well. So I will skip actually a lot of data, but here basically you see we were able to again recover sodium, potassium, calcium, magnesium, and also ions on sodium, on acetate, acetic acid, like lactic acid, and many other things as well, right? Another thing is what we can do is we can again take advantage of the electrochemistry in the system. Again, we produce hydrogen on the cathode. But once you take advantage of the chemistry in there, you have a high pH. Once you amend it with mineral, and you would be able to generate calcium carbonate when you insert CO2. So you actually can make it carbon negative by amending the system with minerals. So basically calcium and magnesium source can be very cheap. and also injecting CO2 from either point source or even concentrated from air CO2. So you actually generate this sort of calcium carbonate precipitate, where people have used this as a construction material. So you can permanently fix CO2 that way. Or alternatively, you don't use abiotic system as a cathode, use bacteria. So you add a bacteria, have many different pathways, but this Wood-Gandal pathway is especially interesting because they would convert CO2 into acetyl-CoA, and then you can tweak what kind of organic chemicals you can produce, which can be very complementary to the inorganic minerals we can produce using the first system, right? So with that said, though, as an environmental engineer, we were thinking, well, can we actually replace the current very energy-intensive wastewater treatment with these new systems where we can, again, still treat the water, remove carbon, nitrogen, phosphorus, but also capture CO2, convert into useful products, and also say we can grow algae to actually also capture CO2 and produce fertilizer and a biofuel like a biodiesel. And we did analysis just based on US and China. You can see in traditional treatment on the left, traditionally it's a carbon emitting process because we do use fossil fuel energy to power the treatment system. But right now, if we actually transform the new process into new process, you actually can capture CO2. It makes it carbon negative. You can actually capture tens of megatons of carbon per year. Then on the revenue generation side, traditionally you don't really recover anything, right? You spend money on your wastewater bill, right? That's it, right? You just spend money. But right now, even though you do have higher spending by building those systems, but you can recover the products. We talk about hydrogen, water, calcium carbonate mineral, and the biofuel, right? So that's sort of things you can generate revenue of that. And where you can apply that, well, it's actually not too hard. If you see a lot of common local locations between a point carbon source, like a power plant or a petroleum refinery and a wastewater, right? So you can basically, okay, take CO2 in and put it into the wastewater treatment plant where they treat like hundreds of millions of gallons of water per day. And then you can actually make the whole system work. With that, I will finish here. And again, this is recording. I hope I would present you live actually in the conference, but just in case this will be the case, I do want to recognize my founding sponsors, the different agencies, industry partners, as well as my group members who really did the awesome work on the different topics. Thank you so much.